we now have all the components we need to try to train the model. So basically all I want to do is aggregate what we did up above. And we're going to do this in a for loop. So let me say they're going to be 1,000 epochs. So like we're going to adjust the weights and bias 1,000 times. So I'll say epochs equals 1,000. And then for I in range epochs. And if it turns out 1,000 is taking too long or is not enough, then I can come back and change it. So we compute this loss, and the reason we want to compute it, like we're not going to look at it at all, but what we're going to do is we're going to use this loss to compute the gradient. Okay, and then we'll use that gradient. The gradient says what changes to the weight and bias increase the loss as much as possible, and then we want to do the opposite. Okay, instead of gradient ascent, we want to do gradient descent. So we're going to move in the opposite direction of the gradient, but that's all automated for us inside this optimizer. So we say if the optimizer is remembering any previous gradients, get rit of them. Okay, now compute the gradient using the loss that we just computed. And then we'll say optimizer.step. And that's going to change the weights and bias. And just for the fun of it, and also to give myself a sense for how fast this is going, let's say every 50 epochs, let's show what the loss is. Okay, which is just going to be a single number, and we hope it's going down in aggregate. So how can I say I want to do something every 50 times? Well, there's a nice way to do this where I can say like 53% sine 50. And that says, what's the remainder? Hey, if you've seen modular arithmetic, this is saying, like, what's 53 modulo 50? Otherwise, you can think of it as the remainder when you divide by 50. So if I do 103 mod 50, I also get 3. And the important thing is that if it's divisible by 50, then you'll get 0 when you do this procedure. So I'll say, if I mod 50 is equal to 0, then let's print the loss. So you can tell that it's extremely fast, and it looks like these are going down. That's good. And it looks like we could even go a little further. So let's do it one more time. And maybe I'll just show every 100 this time. So there should only be 10 printed out now. And so notice how I'm not like resetting the neural network anywhere inside this code block. So that's why I can run this and then run the same thing again and get different results. So like this one is picking up where the previous one left off. And yeah, that all looks pretty good. So let's go back and see what the parameters are now. Okay, well, whatever this means. And like, let's not worry so much about the gradients, but let's pay a little attention to these. So it looks like the two weights are very similar to each other. And then it looks like this is about maybe half or a third the negative value of the weights for the bias. So let's just sort of remember that. And we can also just try plugging in x. Hey, remember x was like our training data. Hey, x was like this length 4 list of data points. And so when I plug this into my neural network, I'm hoping I see something close to 0, 1, 1, 1. Okay, we definitely won't see exactly that. For one reason, sigmoid can never output 0 or 1, but it could output something like 0.00001. So let's see how close this looks. So we're hoping for 0, 1, 1, 1. So 0.1 and then very close to ones. Okay, let's run it one more time. And let's check this again. So these weights got a little bigger And the bias got a little bigger in the negative direction. And let's see if this has gotten closer to 0, 1, 1, 1. So everything was really good except for maybe this first one. Maybe I'd like that to be a little smaller. Okay, so we can tell that this neural network is working well. The optimization part is working well because these, and on one hand, the loss is getting smaller and smaller, which is good. And on the other hand, for such a small data set, I can also see explicitly that it's getting closer and closer to the answers I want. So we can think of this one as saying the neural network is predicting that it's a 97% chance of being true. That's one way to interpret this for the inputs 0, 1, okay, which was this set of inputs. Okay, yeah, that's all I'll do in this video. Thank you for watching.